Well, hey, fellow A&P nerds. It's just me again with a little lecture. This one I like to call, What About All This Potassium Business? So when we talk about action potentials, the depolarization, repolarization of cell membranes, like you have probably learned about with skeletal muscle cells and neurons, we talk all day about voltage-gated potassium ion channels. You can see one of those right here. Voltage-gated sodium ion channels right here. The sodium-potassium pump. But not a lot of attention is typically given to potassium ions, except to say those ion channels are slow, they're sluggish, they open a little too slowly, close a little too slowly, and even cause that potassium undershoot, that brief hyperpolarization we characteristically see in neurons. But there is a potassium problem, a clinical issue we have to address that primarily is of concern to us regarding neurons and cardiac muscle cells. So what you can see here, I've drawn out a little piece of cell membrane for us showing both the extracellular and intracellular areas, the voltage-gated sodium and potassium ion channels, and the good old sodium-potassium pump. Now, you of course remember that the sodium-potassium pump pumps sodiums out of the cell 3 at a time, potassiums into the cell 2 at a time. This is not news to any of you A&P nerds, I'm quite sure. To establish what? A resting membrane potential with a bunch of sodium outside, a bunch of potassium inside. So how about I go ahead and draw some of these ions outside in the extracellular fluid. I'll throw some potassiums out here, or excuse me, some sodiums out here. 1, 2, 3, 4, 5, 6, 7, 8, let's just say 9. 1, I like to circle them to double check my count. 2, 3, 4, 5, 6, 7, 8, 9. So 9 sodiums outside, 2/3 that many potassiums inside, so I guess that would be 6 potassiums on the inside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you can see hopefully that the outside, the extracellular fluid here, as I've drawn it, is more positive than the inside. So I've established a resting membrane potential about negative 85 or 90 millivolts for a skeletal muscle cell, about negative 70 for a neuron. Perfectly fine. We understand all this. This is probably old news to you. But I think we should pay attention to a couple factoids. First of which is the following. There are such things as what we call leak channels. For both sodium and potassium ions. Leak channels are a slang way to describe non-gated, not NAND-gated, non-gated ion channels for these two ions. When exactly are non-gated ion channels open? All the time. When exactly do non-gated ion channels close? They never close. So we have these non-gated ion channels, open doorways for both sodium and potassium. Let me draw a few in related colors. So I'll use this dark blue for my non-gated sodium ion channels. So there's one right there. A non-gated sodium ion channel. So what would stop these sodiums from going through this ion channel to the inside of the cell? Nothing. They would be able to. This door is open. Now let me pick a similar color to my purple. Let's go with plum. Well, plum's going to be awful close to, yeah, that's a little too close. So let me pick a different color. Let's go wildly different. How about orange? That'll stand out. So orange will be my non-gated potassium ion channel. This dark blue is my non-gated sodium ion channel, just to keep us straight. So let's draw in a non-gated potassium ion channel. There's one right there. Oh, but wait, I don't think I drew in enough. Let me draw in some more. Non-gated potassiums. Now look at this, the way I have drawn this. Non-gated sodium ion channels, how many did we have? There's one. Non-gated potassium ion channels, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 non-gated ion channels for potassium, 1 for sodium. Now, I want you to understand, fellow A&P nerds, I exaggerate here, but not the way you think. If I wanted to make this accurate for some of our cells, like cardiac muscle and neurons, if I wanted to make this accurate, I need a lot more than 16 non-gated potassium ion channels. I'm only, what, about 984 short? There can be as many as 1,000 non-gated ion channels for potassium for every 1 non-gated ion channel for sodium. So which one do you think is a problem for our cells? Well, obviously potassium. This is the potassium problem we talk about. So that's what we're going to address right here, is the potassium problem for certain of these tissues. Normally, I want you to consider this for a minute. This is some in-depth physiology we're doing here. Let's say that the voltage-gated potassium and sodium channels are closed. This cell is at rest. The resting membrane potential has been established, right? Everything's fine. See this one sodium door? It's open. What would stop sodium from coming in? Nothing at all. It would come in right through this door. But guess what? Sodium-potassium pump's going to kick it right back out. This doesn't become a huge issue because there are so few of these doors. But what about potassium? The potassium ions could actually go through any of these open doors into the extracellular fluid. And guess what they do? They go through the open doors into the extracellular fluid. So there's this constant leaking, hence the name leak channels, this constant leaking of potassiums where they leak out of my cell. So if the potassium goes, everybody watch, from here to out here, so now this one that was inside is gone. If it goes from here to out here, so now this one is gone. That makes the inside of my cell less positive, doesn't it? This constant leaking. But don't forget what we've established, everyone. This big electrochemical gradient where the outside of the cell carries this net positive charge and a lower positive charge inside the cell. So, keep your brain in the full-on position for me. These potassiums would follow their concentration gradient and leave the cell. But what would the electrical gradient make them want to do? More positive outside, less positive inside. Yes, you get it. They'd want to come back, wouldn't they? So then the potassium might move from here, outside the cell, to back in, inside the cell. I tell people to think of it this way. It's sort of like that adult kid moving away from home. Even more so nowadays, right? So the kid wants to, here's the kid wants to move away from home. You know, what are they going to say to the parents? You know, stop trying to run my life. You know, go ahead, boomer, you live the way you want, but I'm going to live the way I want. I'm moving out. So the kid moves out. Big force for him to move out. But then what happens when they get out here? You know, we're in post-pandemic times. Maybe the economy's not so good. The kids out here, life is tough. I can't afford my own apartment. This is bad. Maybe I need to come back home. So we have this constant movement out and then back in. Out and then back in. So this potassium typically gets cycling around. Goes out through the non-gated channels, comes back in through the non-gated channels, goes out through a non-gated channel. That's what happens in these tissues. So we get this constant cycling around of the potassiums. Move out, move back. Move out, move back. The sodium, by comparison, is relatively insignificant. The problem we have, the potassium problem, comes when we get a situation where there's too much potassium in the extracellular fluid or too little potassium in the extracellular fluid. So I'll jot down a couple definitions for it. First off, let's start with this one. A condition of hyperkalemia. Its opposite, a condition of hypokalemia. Hyper, too much. This is too much extracellular potassium. Extracellular potassium levels are too high. Hypokalemia, not enough extracellular potassium. Extracellular potassium level is too low. So hypo, extracellular potassium level is too low. Hyper, extracellular potassium level is too high. Those of you going on in clinical sciences will learn specific amounts in the blood. What could cause this condition of having too much or too little potassium? Not that it's that important for a first semester AP class, but the hyper, this usually comes from your kidneys are shutting down. You're not urinating enough. You are dehydrated. Some drugs can do this to you, but often this is the kidneys are not working enough and too much potassium is building up in a person's bloodstream. The opposite, hypokalemia, usually comes from the fact that your kidneys are working too much. You're urinating too much. If we have diuretic drugs, drugs that cause us to urinate a lot, then we're losing too much potassium, so our blood potassium gets too low. Typically related to underworking, hyperkalemia, or overworking, hypokalemia, kidneys, along with various metabolic disorders that also could contribute to this. But let's talk about what this does to my cells. Let's talk about the actual potassium problem, why we worry about this so much and guard against it. So if I come back up here to my picture and we look at the extracellular fluid, I'll keep my color code black here. Let's say that for whatever reason, the reason doesn't matter, my extracellular potassium is suddenly too high. There's more potassium out here than is normal. See that? So I'm adding all these potassiums. This is hyperkalemia. Too much extracellular potassium. So here's my question for you people. If now I've established a bunch of potassium on the outside of my cell, would these potassiums inside be more or less likely to leave? Think about it. What drives them out? Their concentration gradient. Originally there was hardly any potassium out here. Now there's a whole bunch. So would these potassiums want to leave? No, they don't want to leave at all, do they? They don't want to leave at all. In fact, do you see how these new potassiums outside would want to go in? They'd move in through these leak channels, wouldn't they? These potassiums would go in. These potassiums moving in, this is the problem with hyperkalemia. So, less potassium would be leaking out of my cells. So in hyperkalemia, too much or an excess of extracellular potassium, this means less potassium leaks out. In fact, some potassium would even leak in. The inside of the cell gets more positive in charge because of all this potassium in there. This is called a slight depolarization of my cell membrane. That's what this causes. Or in other words, the cell gets closer to threshold, if we're talking about a neuron or a cardiac muscle cell. Closer to threshold, more likely to fire, more likely to contract. So the end result is I could have an unwanted AP action potential in this cell. Cardiac arrhythmia. If it's the heart cells contract when they normally would not. I could have unwanted neuron firing. An unwanted action potential once Because do you remember how these cells repolarize, everyone? It's when the potassium leaves. But what did I just tell you about above here? In hyperkalemia, do the potassiums inside my cell want to leave my cell? No, in fact, they won't leave my cell. So, this idea of hyperkalemia, I could get an unwanted action potential one time, but it interferes with repolarization, so I can't get the thing to fire again. That's not good, is it? I can't have the cell, the neuron or the cardiac muscle cell, recover. Well, now let's talk a little bit about hypokalemia, when my extracellular potassium level is too low. So moving back up to my picture here, give me just a moment, everyone, to erase my extracellular potassiums. Let's say I take them all away. There's no more. I'll erase the kid moving away from home. There's no extracellular potassium at all. My kidneys are working too much. And whatever potassiums I have that do leave, everyone, what potassiums I have that do leave, let's say this one leaves. Guess what happens? I urinate it out. So not only did it leave my cell, but it leaves my extracellular fluid as well. So this one over here, it leaves my cell. So it's no longer inside. But guess what? Then I urinate it out. In this scenario, the potassiums inside the cell are more likely to leave, aren't they? Think about it, it would be exactly the opposite of hyperkalemia. So hypokalemia, not enough extracellular potassium. In this condition, more potassium leaks out of the cell. The inside of the cell, the intracellular fluid, gets less positive. A slight hyperpolarization, we call this. Or farther from, if you like that better, farther from threshold. So now the cell is less likely to fire, less likely to contract. Or in English, can't get one action potential, can't get even one. Can't get the first action potential to happen, let alone go for a second. I can't make it contract. So the cardiac muscle cell won't contract, the neuron won't fire. Cardiac muscle cell won't contract. The neuron won't fire. This is a problem, isn't it? Either one of these conditions can become seriously life-threatening very quickly. Think about it for just a moment with me, and let's say we were talking about your heart. Let's just pick on the heart. We could use the brain or the spinal cord too, but let's say it's your heart right there. I'll draw you a little Valentine heart. So your heart is going along beating as it does, sort of something like this. Now, people who aren't in one of my lectures, that isn't actually my heart or an amplified heart sound. I'm just making that noise in my throat. But normal heart rate, right? And let's say you suddenly experience hyperkalemia because your kidneys are failing. They're not working. So suddenly you get hyperkalemic. Now you'll get an unwanted action potential in your cardiac muscle once and then not again. So a little cardiac arrhythmia before your heart stops. So something like this. Normal first. Then a little hiccup. And then nothing. How do you like that? That's not good, is it? That could kill you. What about hypokalemia? What about hypokalemia? In hypokalemia, your heart's going along beating as it normally does. And then you suddenly become hypokalemic because you've urinated out too much potassium, and now your heart simply stops without the hiccup. Also very bad. Do you see how either one of these conditions could kill you? On the left-hand side, hyperkalemia, the unwanted action potential, let's say cardiac muscle contraction, once a little hiccup and then nothing because you can't repolarize. Death. How about hypokalemic? All of a sudden, no contraction at all. Death. Either one could be potentially dangerous, right? So this is the potassium problem. Now, just a little clinical trivia for you as we go back up here and look at our picture. Once in a while, if you take a blood sample from someone and you're a little rough with them, meaning their blood vessels and their blood cells. So let me redraw in my potassiums that would have been in here. Let's see, I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9. So 6, 1, 2, 3, 4, 5, 6. So let's say it's perfectly normal, resting membrane potential, no hypokalemia. If you take a blood sample from someone, and while you're doing it, maybe you squeeze a little too hard. Here's a red blood cell for you. This red blood cell has a bunch of potassiums inside, and if you rupture the red blood cell, if you destroy the cell membrane, a bunch of potassium leaks out because you blew up the cell. You could get sort of a false hyperkalemia reading because you tore open cell membranes and a bunch of potassium leaked out. So if a person is suspicious of that, they typically will run, another blood test for that. But this is the potassium problem. Too much, bad. Too little, also bad. Hypokalemia could drive a person into death fairly easily. Why? So many leak channels for potassium. This is the potassium problem.